Swayam Prabha. Digital India. Educated India.
Well, let me continue what I have done in the previous lecture. That in the previous lecture I have discussed about the stability chart method, which can be used. The chart can be used to find out the factor of safety quickly. In fact, there are a number of methods are available. We have discussed only a few. And in fact, at present, since earlier when there was no computer, people used to do by hand calculation, all rigorous calculation people used to do by hand. But now, and when we do by hand also, we had a restriction. That means we cannot handle too many complicated slope or irregular slope, only homogeneous and plain slope only we could handle. So, because of this, but actual slope in nature, particularly natural slope and all, they are quite complex, and because of that people actually try to use more advanced method, and of course, there are few methods, several methods are available, and finally, those methods are computerized. That means, it is programmed, and if you give the proper input, that means say geometry of the slope and the soil property, and it will calculate and give you the factor of safety. These are actually rigorous method. Before going to that, I will just take one problem which I have just completed in the previous lecture, that is using Taylor's stability chart. So, this problem is something like this. An embankment has a slope of 1 vertical to 2 horizontal, and the properties of the soil C equal 25 and phi is 20 degrees, and gamma equal to 16 kilonewton per meter cube, and H equal to 31. That means, your slope 1 vertical 2 horizontal. So, something like this. So, this is 1 and this is 2, 1 vertical 2 horizontal. The slope was like this, and this property of the slope material embankment C equal to 25 and phi equal to 20 and gamma equal to 16, and this height of the slope is 31 meter. 31 meter. Now, using Taylor's chart, I have to find out what is the value of factor of safety for this slope. So, let me start that, and of course, I have not included in this chart. Better I will do, I will bring the chart, or I will open another file. Stability number n equal to C by gamma h, and that will be your no. So, I will not do that. What I will do? I will do for phi equal to 20 degrees and slope angle, actually 1 vertical 2 horizontal, corresponding to it gives you alpha equal to 26 degrees 30 minutes. So, that means this slope 26 degrees 30 minutes. So, this is actually, I think it is written as beta. So, this beta equal to this and phi equal to this, and if I refer chart, then I will get n equal to value actually 0.007. Okay. And sorry, not 0.007, this perhaps 0.07. If I will go back to that chart once again, and then I know this is equal to C by gamma h. Then from here I get C equal to I get 0.07 multiplied by 16 multiplied by 31. So, that is equal to 8.43. 8.43 kilonewton per meter square, but this is not the factor of safety, mainly because when if the value of phi also, when you calculate factor of safety, both in the phi component and in the C component factor of safety should be there, but when it is phi is assumed 1, factor of safety is as 1, then only it is value is coming like this, but this is not the actual calculation. Our calculation was F equal to shear strength divided by disturbing shear, and that is actually shear strength is C plus sigma tan phi, and this is actually tau. Okay. So, your tau will be equal to C by F plus sigma tan phi by F. Okay. So, that means you have to, and this F and this F should be same. So, if I do this way, then what I will do, I can assume a factor of safety, and then I can find out this one, and then correspondingly I can find out value of C and then find out the factor of safety. If I do that, now I will try with F equal to suppose 1.5, and then I can find out sigma tan phi by 1.5, that means sigma sorry, not sigma tan phi, but tan phi by 1.5. If I reduce, then it become tan 20 degrees by 1.5, and that gives you 0.242, and which can be equal to which gives you tan phi equal to 13.5 degrees. Now, this tan, as I have told you, by introducing factor of safety, I am reducing the value of phi. Now, with this value of phi equal to 13.5 degrees and beta equal to 26 degrees 30 minutes, and then I refer the chart, and then I will get a value of n, and that time you get a n value equal to 0.047. So, if I get the n value this, that is again C by gamma h, and from there I will get C value will be equal to 23.3, and then your factor of safety for C will be, actual value available is 25, and here actually mobile is 23.3. So, factor of safety is 1.07, and this 1.7 factor of safety we are getting for C, and we have assumed factor of safety for phi as 1.5. So, this is not equal to 1.5. This is not equal to 1.5. So, our actually, if based on this assumption of phi factor of safety in phi 1.5, you have reduced value of phi, and then that reduced value of phi and beta you refer the chart, and then get the value of n, that is getting 0.047, and then that value, if I refer to this, then if I refer to equate C by gamma h, then you get a C value of this. From this C value, and actual C value available is 25, then I am getting a factor of safety of 1.07, but which is different from the assumption 1.5. That means, my assumption is not correct. The factor of safety actual available is something different than that. So, because of that, so that means this calculation will not correct. So, what I will do again, I will be doing another assumption, that means I can change the factor of safety now. Factor of safety I will change to 1.35 suppose, or so suppose 1.3 factor of safety, suppose 1.3 I assume, and then your tan phi by 1.3 equal to tan 20 by 1.3, that comes 0.28, and that gives you tan phi equal to, or that gives you tan phi equal to 0.28. If I do, then phi you get actually 15.75. 15.75. Now, phi equal to 15.75 and beta equal to 26 degree 30 minutes and refer chart, then I will get a n value equal to, equal to 0.036, and this gives you C equal to C will be equal to 0.036 multiplied by 16 multiplied by 31, and your then factor of safety for C will be equal to, value available is 25 divided by 0.036 multiplied by 16 multiplied by 31. So, that gives you a value equal to 1.4. So, which is not equal to again 1.3. So, I will now I will assume another factor of safety equal to 1.35, then your tan phi by 1.35, that gives you 0.27. From there I get phi equal to 15 degrees. Now, phi equal to 15 degrees and beta equal to 26 degree 30 minutes, and from chart I will get n equal to 0.037. Then your, and that from this one will give you C equal to 0.037 multiplied by 16 multiplied by 31. Then factor of safety for cohesion will be value available 25 divided by 0.037 multiplied by 16 multiplied by 31, and that gives you 1.36. It is quite close to 1.35 cents. Okay. So, that means for the particular slope which we have used, that slope for that slope your factor of safety, that is slope with one vertical, two horizontal, and with value of phi equal to 20 degrees and gamma equal to 16 and height 31, the factor of safety comes out to be 1.35. So, this is the problem asked actually. So, we have to do a trial and error method, that means you assume certain value of factor of safety, and then if it is does not match with the factor of safety finally, then you have to modify it and do the process until you get a convergent result. So, this is the way. So, 1.36 and 1.35 they are quite close. We are assuming that we have reached to a value which is acceptable. So, the finally we can say that factor of safety for this slope is 1.35. So, this stability chart actually I will refer back once again if necessary. So, now next thing is that rigorous method, and in the rigorous method actually first introduced by Bishop, and Bishop's conventional method actually use effective stress method, and figure, and the next slide, that is a figure actually one particular slice will be shown, and on that slice what are the forces acting, it is shown, and then we will see that finally the slope that slice is statically indeterminate, and to make it statically determinate some assumption was made, and based on that finally he derived the factor of safety expression for a complicated slope, something like this. So, if you better I will go to the next slide. So, this is the slope, suppose this is the slope, and then on this slope there is a slice taken, suppose one slice is taken here, and on that slice what are the forces acting? This self weight of the slice it is acting. Then from the left side there will be force acting from the left side, and from the right side there will be some force acting, and there will be tangential force acting, there is a normal force acting. So, all those forces are actually until unless if you assume these two, if I keep these two unknown, then your problem will not be able to solve. So, Bishop actually assumed this and this actually equal, and based on that and then doing all those calculation stability and all, he has got the expression for factor of safety factor of safety equation is like this. So, here in this actually you can see each slice W to be calculated, W sin alpha to be calculated for each slice, and then summation to be taken, and this is actually C dash the cohesion effective stress cohesive part, and the L actually length of the slice, and then again W cos alpha, then you can find out the pore pressure at the point, and this is the again there is a angle component, and then tan phi dash. So, all those things then for each slice it has to be obtained, and then finally it has to be summed out. Okay. So, then after this is a total resistance and this is total disturbance, and then you will get the factor of safety from this. And if I use this method, generally it is noted that you will get a some difference and from error, and this error actually in favorable side, actually it estimates. So, the solution given is known as Bishop's conventional method, and it gives error up to 15% in the value of f obtained. So, and 15% error in the value of f. However, the error is on the safer side, since it gives a lower value of value than it is actual. So, Bishop's that conventional method, whatever we have recommended, generally it gives you a lower value factor of safety, which is actually safer. So, because of that, but always safe is not expected, you have to think about the economy also. So, because of that further investigation was carried out, and then Bishop further modified his solution, and he gave a final expression that is called Bishop's modified method, and in this he has given an expression again. You can see this expression is a big expression, and in this the surprisingly you can see both sides of the equation having f factor of safety. So, that means what you have to do, we cannot find out factor of safety just like that, you have to trial and error. So, you have to assume value of factor of safety and then do the entire calculation, then find out what is the final factor of safety. So, these two finally it has to be matched, like by while doing using stability chart we have done. Similar way here you have to start with a factor of safety, and then you have to again final factor of safety you have to find out, and you can see the number of things are there which are all known. These are actually width of the slice, this is C cohesion, this is W weight of the slice, this is a pore pressure, all those things for each slope has to be calculated. And so, this calculation before coming the computer so easily, because this is developed in 50s or 60s, So that time computer was not readily available, and the performance of also was not so fast, but people used to do by hand calculation, and that hand calculation is quite rigorous. So, so that calculation to do this calculation by hand, people used to follow a particular method or steps. So, this hand calculation is quite rigorous, one has to do by using a table, and then table calculation generally. So, you have several component, each by one by one you calculate in the tabular form, and finally, left side factor of safety, right side factor of safety. When it match, then you will satisfy that you get the actual factor of safety. And in fact, presently this calculation hardly people will be doing by hand calculation. It is generally not generally, it is commonly it is software available. Actually, the whatever the steps we follow in hand calculation, that is actually instructed in the program, and then if you give the geometry and certain soil parameter, all soil parameter, relevant soil parameters, then it gives you the factor of safety. So, this is the one method, but somehow this since I will not be able to introduce the software part, and so this Bishop's method, that is either conventional or modified method, is out of the scope. So, I will not this is of course problems etc. I will not solve by this method. Already whatever possible within hand calculation, by hand calculation I have already explained, and this Bishop method only for introducing that there is some method which is very accurate and reasonably accurate, and also applicable to all situations. That means, any slope, whether it is natural or man made, any irregular, non homogeneous, with pore water, without pore water, with water table, no water table, any combination, actually the slope is there, this calculation can be done by program. And so, this is actually a method available and in commercially softwares available. So, people can use it, and other than that there are other methods also. So, I will not discuss that, I will stop here. Only thing, I could not show the table on this, somehow let me see whether in the last one I can show that, otherwise I will stop here, and thank you.